For this example, a population is growing so that after 1 year, the population has increased by 10%. Assuming that the population grows at a rate proportional to the current population size, how many years will it take for the population to double? So for this problem, we need to identify first our variables, and then we need to identify a model. So for our variables, we are interested in our population, and our population changes in time. And so we need two variables. Population variable, let's use P, and for time, let's use T, and we'll measure this in years. Now, for a model, we need to identify what kind of model would be appropriate. The key is that it tells us that the population grows at a rate that is proportional to the current population size. And when I put those three things together, this is telling me that the rate of change, that's a derivative, the rate of change for my population is proportional to the population size, which means that I can create an equation. The rate of change of my population with respect to time is equal to some constant times p. And as soon as I know that my derivative is equal to a constant times p, that's exactly what we mean when we have an exponential model. My population can be written as an exponential function of time. See, if I take a derivative of my population variable, dp dt, I have a constant, a, times the derivative of an exponential. And the derivative of an exponential is itself, e to the kt, times the derivative of the exponent, kt. The derivative of kt is the constant, k. So I get the rate of change for my population is k times the original population. And so now I know my model. Next, we need to look at what information we're given. Our given information is that after 1 year, the population has increased by 10%. So this is a comparison of two different times. What we're saying is that if I compare my population at time 1 year, and I compare that to the population at time 0 years, the population at time 1 is 110% of the original. So it's 1.1 times the population at time 0. What we'll do now is we'll use our model and think of my population at time 1 through the model. A, e to the k, t, and t is 1. This will equal 1.1 times the population at 0. Again, a, e to the k, t, except this time my time is 0. This equation that comes from my given information allows me to solve for my constant k. Notice that a cancels, e to the k times 0 can be replaced by 1, and so I get an equation, e to the k equals 1.1. I can now solve for k using logarithms. K must then be the logarithm, the natural logarithm, of 1.1. This allows me to write my model for my population. A, e to the k, natural log of 1.1, times t. Notice, by the way, that this is the same as a times 1.1 raised to the t. This is the form of a b to the t. Finally, now that I have that, I've used my given information, let's identify what is wanted. We want to know how long for it to double. How long to double. In other words, we want to know what time will make it so that the population at that time is double the population at time 0. Again, I use my model, a e to the k, natural log of 1.1, t is equal to double the population at 0. a e to the k, natural log of 1.1, times 0. Again, the a cancels. The natural log of 1.1 times 0 is 0, so this term goes to 1, leaving me with an equation, e to the natural log of 1.1 t equals 2. If I did ab to the t version, this would be saying 1.1 to the t equals 2. When I take the natural log of both sides, I get the natural log of 1.1 times t equals the natural log of 2. This allows me to solve for t. T is the natural log of 2. In other words, that's the doubling divided by the natural log of 1.1, and that's the time it takes to go up by 10%. Using a calculator, we find that this is approximately 7.2725. So my population doubles every 7.273 years. Focusing on the big picture, we identified our variables. Using information about the rate of change being proportional to the population, we were able to come up with a model. This model, we took our information, that allowed us to solve for our coefficients, our parameters. A didn't matter for this model because we actually didn't need to know the size of the population. We only needed to know how long it took to reach some ratio, the doubling. I could then solve that using equations and natural logarithms to find the actual time.